Experimental proof of the atomic theory was one of the great triumphs of 20th century science. There was a convergence of so many different lines of evidence. The chemists' laws of combination. Physicists' studies of Brownian motion and of radioactivity. You had the discovery of X-rays and the determination of X-ray crystal structures. And of course, actual images of atoms with atomic microscopy. These studies left little doubt that atoms were much more than a useful fiction. Atoms are real. But in order to understand the behavior of atoms, we have to introduce a remarkable and a counterintuitive model called the Bohr atom. And we have to introduce the great principle that electrons in atoms adopt stable orbits at specific energies. In this lecture, the 18th of my series, I focus on the curious behavior of electrons. Electrons in orbit around the nucleus of an atom. First, I'm going to introduce to you the Bohr atom. Then we're going to consider the nature of light-matter interactions at the atomic level. And finally, I'm going to tell you about the transforming modern technologies of spectroscopy and the laser. In the last lecture, we saw that Ernest Rutherford had a concept of the atom. It was that you had a central, massive, positively charged nucleus, and around that nucleus traveled swift, light, negatively charged electrons. This model was simple. This model was elegant. It was also absolutely impossible. Just as an Earth-bound satellite, which is in the atmosphere, must eventually lose energy and spiral in, crashing to the Earth, so must Rutherford's electrons crash into the nucleus of the atom. And this is why. Electrons in orbit are negatively charged, and because they're rotating around, they're constantly accelerating, according to Newton's first law. Remember, acceleration, a change of direction. So if you go around in orbit, you must be accelerating. But remember what Maxwell's equation said. If you accelerate a charge, then you're going to produce magnetic fields. You're going to release energy. Photons are going to have to move away. Remember, you wiggle an electron, photons, energy radiates out from the particle. And so think about the Rutherford atom. That orbiting electron has to be sending out photons, and so it's sending out energy. The electron has to crash into the nucleus. And indeed, if you do the calculation, the Rutherford atom cannot survive for even a second. A possible solution to this dilemma was proposed by the Danish physicist Niels Bohr, who lived from 1885 to 1962. Bohr was one of the most influential scientists who's ever lived. He was born in Copenhagen. He grew up in a rich intellectual environment. His father was a professor of physiology at the University of Copenhagen. His mother was from a family of distinguished educators. So Niels and his brother Harold, who became a famous mathematician, by the way, took full advantage of these opportunities of their educated household. Niels and his brother studied physics and mathematics at the university with faculty who were also close family friends. And by his mid-20s, Niels had earned a doctorate, and he had also won a gold medal for his studies from the Danish Academy. Very distinguished early career. In 1912, he joined Ernest Rutherford's group at Manchester, and he began to work on the atomic theory. These were the studies that led to his Nobel Prize in 1922. Bohr accepted many administrative responsibilities as well, so as a scientist, he also contributed to the social structure, if you will, of the scientific community. For example, he was director of the Danish Institute for Theoretical Physics. He was president of the Danish Academy. He was founding director of the Nordic Institute for Theoretical Physics. During World War II, he was able to escape to the United States, and he participated in the Manhattan Project that built the atomic bomb. He was indeed one of the very first people to express the very optimistic and the perhaps naive view that the mere development of nuclear weapons might put an end to war altogether, because it was so unthinkable that anyone would use nuclear weapons. Bohr was also a founding member of the Danish Atomic Energy Commission, which occurred just after the war. Niels Bohr was so celebrated in Denmark that he was given a mansion in Copenhagen. He was awarded his own grand residence. And I've been told that one of the special features of this mansion is that it actually had a tap in the kitchen which was connected directly to the brewery, and you turn on the tap and out came beer directly from the brewery. I don't know if it's true, but it's certainly a great story. Well, you get the idea. Niels Bohr was admired in his day. He achieved an unusual position of influence in the scientific community. It was while he was working in England in 1913 that he developed this atomic model, this strange and counterintuitive model called the Bohr atom. By the way, this is not the boring atom, as some of my students have tried to tell me. It's really absolutely fascinating and counterintuitive example. Bear with me, because the whole concept of an atom in which electrons do these strange things that Bohr said is really quite marvelous. It's unlike anything we experience in life. He developed the model after studying the way glowing hot hydrogen gives off light. When you light a light bulb, an incandescent light bulb, it gives off all the different wavelengths of light. As that filament heats up, reds and yellows and oranges and blue, all the different wavelengths come out of that light bulb because of the hot filament. But when you heat glowing hydrogen, when you take hydrogen gas and heat it to a high temperature so that it becomes incandescent, you see something rather different. You see discrete wavelengths, a line in the red of just one wavelength. There may be a line in the blue and the yellow and maybe some other lines, each one with a very specific wavelength. Bohr suggested that this implies that electrons have to adopt very specific energy levels in an atom. Rather than being at any possible level, you see very specific energy levels, and that these lines in glowing hydrogen represent times when electrons jump from a higher energy, the charged particle going from a high energy to a low energy, and as a consequence emit a photon of visible light at those very specific wavelengths. So here's the Bohr atom. Electrons can reside in several different discrete stationary states, each of which are rather inappropriately called allowed orbits. And these are at well-defined distances from the nucleus. You have a nucleus, then you have an orbit, and another one, and another one, and another one, in kind of a set of stair steps. An electron can remain in one orbit for a long time without accelerating. It just sits there as a sort of a station, like it's resting in a stationary state. And thus it doesn't have to give off light. It doesn't have to give off energy, and so the atom becomes stable. Light is only emitted when an electron jumps from a higher level down to a lower energy level, and the conservation, the first law, tells us you have to conserve energy, so the energy that you lose jumping from here to here is emitted as a photon. The lowest energy orbit of an atom, like the hydrogen atom, is called the ground state. You can't go any lower than the ground state. That's the lowest energy the electron can have. All the higher energy states are called excited states. As electrons hop from state to state, back and forth, specific wavelengths are either absorbed or emitted by that atom. This Bohr atom is not in any way intuitively obvious. It sort of lies completely outside any sort of natural experience that we have in everyday life. In our lives, energy comes as a continuum. You can turn up and turn down the volume of your radio. You can turn up or turn down the amount of brightness of a light if you have a dimmer. You see all continuous sort of range of energies in our life. But at the level of the atom, you don't have a continuous range, you have discrete steps. Even though it's strange, I think I can make some analogies that may make the Bohr atom a little more meaningful to you. For one thing, the energy levels of a Bohr atom are something like stair steps. You place an object stably on one step, or another step, or another step. Just as the different orbits of a Bohr atom have different energies, so when you place an object on different steps, the higher the step is, the more gravitational potential energy that particular object will have. But unlike stair steps, electrons don't move from one orbit to another. You don't sort of move an object from one step to another, but rather the electron literally vanishes from one orbit and reappears in the next. So that's quite counterintuitive. It's hard to imagine how that could happen. The Bohr atom is not like a miniature solar system. In a solar system, a planet can be at any distance from the sun. The Earth could be 1,000 miles closer or 10,000 miles farther away, or any distance at all, and it would achieve a stable orbit. But in a Bohr atom, you have only very specific distances from the nucleus that the electron can occupy. Furthermore, planets in their elliptical orbits are constantly accelerating. They're accelerating because the force of gravity is constantly pulling them in towards the sun. But in the Bohr atom, these electrons are not accelerating. They're in stable orbits. They're just sitting there. It's like an object sitting on a table. But in this case, it's the orbits, the electrons sitting in their orbits. So that's quite different as well. In spite of the strangeness, the Bohr atom was embraced by physicists because it was extremely successful in modeling the behavior of atoms, especially things like the way an atom interacted with light. For example, when you heat up hydrogen, this emission of the line spectra, the specific wavelengths, was very significant, and the Bohr atom successfully explained it. I think, indeed, the strangeness of the atom mirrors the strangeness of the world at the subatomic level. And we're going to see in the next lecture on quantum mechanics that the strangeness doesn't just end with the Bohr atom. It goes on beyond that. It was for all of this work on the atom that Niels Bohr won the 1922 Nobel Prize in Physics, and that was just one of his many, many honors. The Bohr model of the atom helps explain light-matter interactions, and I want to look at these light-matter interactions for a while. The model postulates that energy and light must come in discrete packets, discrete bundles called quanta. The smallest possible increment in energy is called a quantum jump or a quantum leap. That's when the electron moves from one energy level to the other. I'm often amused at the misuse of this term quantum leap. Think about it. An advertiser will say, "We've made a quantum leap in technology." And you think about it, the quantum leap is absolutely the smallest increment possible in the universe. So, well, who figures? Anyway, that's the vernacular it's come to be known. A quantum jump from a higher energy level to a lower energy level releases one quantum of electromagnetic radiation. That's called a photon. And so light moves out as the electron jumps down. A single photon, a single wave of electromagnetic radiation radiates out. It radiates out at 186,000 miles per second, and it has a wavelength. It has an energy that corresponds to that difference between the one state and the other state. When you observe a glowing light bulb or a flame in a fire, you're seeing cascades of excited electrons dropping down. As you heat up the object, the electrons are moved into excited states, and they start dropping down, moving up, dropping down. And every time the electrons drop down, they emit some wavelength of light. And that's what you see in a light bulb, in an incandescent bulb. Remember, electromagnetic radiation is a continuous spectrum. So not only does one of these light bulbs produce visible light, it also produces heat, infrared. And that's why an incandescent bulb is also very hot, because you're producing the longer wavelengths of radiation that we feel as heat. When an atom absorbs a photon, an electron jumps to a higher energy state. So, for example, when black asphalt is bathed by sunlight, the asphalt's soaking up the sun's energy. That means electrons are moving up into excited states. They also have much more energy. The atoms get hot, and part of that energy that the black top absorbs is re-radiated out in longer wavelengths as heat energy, and that's why the black top feels hot. Another example of this phenomenon is fluorescence. This is by which a material is subject to ultraviolet light, which is invisible to our eyes. It's a higher energy radiation. And when you subject materials to that, electrons are bumped up to a higher energy level, and then they may drop down back to the ground state in 2 or 3 jumps. Now, ultraviolet radiation, the higher energy, represents the first jump. But the individual steps down might be in the visible light. That much energy might just be a visible wavelength, and so we see the fluorescence phenomenon. And so if you take a material that's fluorescent, I showed you these in the last lecture, the idea is something that looks just sort of dull or white. If you shine ultraviolet light on it, the electrons in these materials are moved into an excited state. They cascade down in 2 or 3 increments, and one of those increments then involves a visible light. So under fluorescent light, these materials appear brightly colored, the bright oranges, the bright greens that you see in fluorescent material. The exact same thing happens in day-glow colors. Day-glow colors occur even with, for example, a blue or violet light, high-energy visible light, or perhaps the very longest wave ultraviolet light that you just have in normal lights or from sunlight. And when that light hits these materials, they re-emit very intense photons in one particular wavelength. And so day-glow colors appear unusually bright. It's a kind of fluorescence phenomenon that you see every day. You're actually seeing a quantum phenomenon just in your everyday life. Other examples of quantum effects that you see all around you, mercury vapor lamps, for example, with their distinctive bluish-white glow. The bright yellow of sodium vapor lamps are other examples of quantum leaps. Now at this point I want to shift gears and look at one of the central methods of modern science. That's called spectroscopy. Spectroscopy is the study in great detail of these light-matter interactions. Spectroscopy is proven to be absolutely essential to all sorts of modern sciences and technologies. It's used in astronomy, it's used in biology, it's used in chemistry, it's used a great deal in environmental science to monitor the atmosphere and monitor waters. The Bohr model of the atom reveals that the way a material absorbs light is dependent on the orbits of its electrons. So wavelengths of absorbed light and wavelengths of emitted light correspond to quantum jumps, and spectroscopy therefore is providing you a direct probe of this atomic scale interaction, because spectroscopy measures the wavelength of electromagnetic radiation and also the intensity. So for any given wavelength, for example, red light or green light or blue light or ultraviolet light, what is the intensity that's absorbed or emitted by a material? That's the science of spectroscopy. A spectrum, or sometimes called a spectrograph, is just a graphical record of light intensity, usually on the vertical scale, versus wavelength on a horizontal scale. Sometimes instead of wavelength, you'll see frequency on one of these spectrographs, but remember, wavelength and frequency are inversely proportional, so it's really the same thing. Typically, a spectrograph will just show a small subset of the whole electromagnetic spectrum. For example, if you have a visible light spectrum, you then are looking at from 400 to 750 billionths of a meter. That's the range of wavelengths, and you'll have an intensity scale on the vertical. The y-axis of the graph, this graph that indicates intensity, is of course usually a relative scale. And what you'll find is that different wavelengths are absorbed or emitted by a material in different intensities. So the graph of wavelength versus intensity is generally going to have peaks and valleys. It may have spikes. It may have very broad features. But in general, it's going to have a variation with wavelength, because almost any object you looked at emits or absorbs light differently at different wavelengths. Spectra are measured with a device called a spectroscope. That measures the intensity of light, and it separates light into the different wavelengths. There are all kinds of specialized techniques to measure spectra in all parts of the electromagnetic spectrum. You can measure radio spectra. In fact, your radio does exactly that. Your radio, as you turn your dial, you're measuring the spectrum of radio waves at different frequencies. And you hear intensity at certain places. Those are the stations that are broadcasting. But you can do this for all the different wavelengths. When I was in junior high school, my father helped me construct a homemade spectroscope. And it's very simple, very crude, but it's exactly like the more complicated spectra, at least in spectroscopes, at least in principle. Light enters one end, and there's a lens that focuses that light. And then right at the central portion where there's a bend in the tube, you have either a prism, or in this case what's called a diffraction grating. You actually have a very fine set of lines that are inscribed on a piece of glass that splits the light into rainbow colors. And then the different wavelengths spread out, they fan out, and at the other end you see that whole rainbow of colors. If you take this spectroscope and look at glowing hydrogen gas, for example, or a neon bulb, what you see is not a continuous spectrum of light, but rather sharp, bright lines of different wavelengths that have been spread out by the spectroscope. There's several different kinds of spectra that are important in research. Glowing objects, that includes incandescent light bulbs and fires, stars, for example, they produce what's called an emission spectrum. In all these objects, different wavelengths are emitted. They're produced in different intensity by the object itself, and you can measure the different wavelengths as a function of intensity. If you look at incandescent light bulbs, you'll see they produce a very continuous, smooth curve of intensities. More intense in the infrared radiation in the red end, less intense in the blue end. Glowing gases produce line spectra, I've indicated. A laser produces just a single sharp, bright line. It turns out that emission spectra are extremely important in the history of chemistry. One of the very first applications of spectroscopy was the study of what are called flame spectra. See, each chemical element has its own distinct set of lines that correspond to those electron levels. So if you heat up an element, it's going to glow in its own characteristic way. And many new elements were discovered using emission spectra in the 1870s and the 1880s. Studies of stars and other astronomical objects would be impossible without this kind of spectroscopy, because each star has its own line spectrum, and then in fact that line spectrum tells us the composition of the stars, it tells us the heat of the star and so forth. These studies had a profound consequence of demonstrating for once and for all that stars are made of the same chemical elements that occur on the Earth. For example, the sun is made primarily of hydrogen and helium. That was interesting. Helium was actually discovered as an element in the sun. It was first discovered by the spectrum of the sun, the distinctive lines that helium produce. And then it was identified on Earth after that. Now, there's also absorption spectra. If light passes through a transparent medium, such as a gemstone or colored glass or even air, the result is an absorption spectrum. Many solids absorb some wavelengths of light preferentially to other wavelengths. Red rubies, for example. Red rubies absorb a lot of the green light. Green emeralds absorb a lot of the red light, and so what you see is the complementary color coming through that gemstone. Hydrogen gas absorbs a whole bunch of wavelengths too. In fact, hydrogen gas absorbs the exact same wavelengths that you see in the emission spectrum, because those are the wavelengths that allow electrons to jump up to higher levels and then they come back down. So hydrogen has that kind of absorption spectrum, and the absorption spectra of elements mirrors their emission spectrum when they're heated up. Absorption spectra are used in all sorts of technological ways. For example, they reveal pollutants in the atmosphere, and they're very critical for environmental monitoring. All different valuable gemstones, if you have a diamond, if you have a ruby, it's probably been monitored, it's probably been checked by spectroscopy to make sure that it's authentic, to make sure it's a natural and not a synthetic stone, for example. Even slight impurities can cause major changes in absorption spectra. Red rubies have only a fraction of a percent of chromium in what is normally a colorless mineral. Spectra can also be obtained by reflecting light off the surface of an object. This is called reflectance spectroscopy. You don't get nearly as clean or as precise a spectra in this way, but it is very, very important in astronomy, because with reflectance spectra you can actually orbit a satellite above a planet or a moon, and you can, by reflectance spectra, learn something about the composition of the surface. You may have read articles recently that many satellites are now orbiting Mars and the Moon and have determined some exciting new findings. For example, the discovery of possibility of water at the poles of the Moon. That was discovered by reflectance spectroscopy. Spectra of all these different kinds of common objects revealed that our eyes and our brain perceive and interpret many different kinds of emission and absorption and reflection phenomenon as the colors. The natural world is much more complex than our eyes and our brain can interpret, so we simplify, and things we call red or green or blue really arise from a very complex, different phenomenon. We perceive white light, for example, as the presence of equal intensities of blue and green and red light, for example. We can perceive red as both the excess of red photons, or an absence of green photons, or an object that just has slightly more red photons than green photons coming into our eye, or a pure red wavelength like a laser light. There are many different things that we perceive as red. They all look red to us, and yet they're produced by many different kinds of physical phenomena. The spectra look very, very different. By the way, partial color blindness results from defects in any of the three types of cones we have in our eye. Our eyes can perceive cones of blue or green or red, and any defect in any of those three is going to cause partial color blindness. So even though we can only detect three wavelengths, if you will, and if you have one of those defective, it really limits your ability to understand the colors that are around you. For the last few minutes of this lecture, I want to tell you about the laser, which is one of the great technological advances of our time. It's resulted in so many technologies, so many military, industrial, scientific applications, and it's a consequence of our newfound understanding of the atom. LASER is an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. The three principal components of a laser are, first, a collection of atoms that have one dominant quantum jump, one principal quantum jump. That's the characteristic color of the laser. Then you have to have a source of energy to stimulate these atoms and get them into an excited state. And then third, a pair of parallel mirrors. And that's so you can align the resultant light and make it into a single pencil-thin beam. The collection of atoms that you start with can be a gas, it can be a liquid, it can be a crystal. The common red lasers that you use for lecture pointers, the kind that I'm sure you've all seen, this kind uses a ruby crystal, a tiny ruby crystal. The red wavelength corresponds exactly to the energy of the quantum jump in that ruby crystal, specifically in the chromium atoms that are a small fraction of the atoms in that ruby crystal. You need electrical energy when you plug in the laser, or you need a battery of some sort, and this pumps the atoms into their excited state. You keep adding energy, and it raises the electrons to the excited state. At first, just a few electrons drop down and produce that red wavelength, for example. But then those red photons, those red wavelengths, start cascading. And they pulse, and they stimulate other electrons into cascading in the same way. And eventually you get a crescendo of more and more, a cascade of photons, all of the same wavelength. And then you have the two mirrors. The two mirrors align the photons, so the photons are bouncing back and forth. But one of those mirrors is slightly transparent. It may be 95% reflective, but 5% of the photons are allowed to pass through, and that's the laser beam that comes shooting out of the laser. I want you to think about the difference between a laser light and a flashlight. There are three major differences. A flashlight emits white light, all the different wavelengths, whereas a laser light emits a single wavelength of red radiation. That's one important difference. The second thing is a flashlight emits a cone of light. The flashlight illuminates a fairly wide area, but a laser light has a spot, a single spot. In fact, a laser light is so focused that you can shine a laser from the surface of the Earth to the moon, and it'll actually bounce back. It'll only irradiate a small area on the surface of the moon. So you can use lasers to measure distances over very, very long distances, like the Earth to the moon distance. And a third difference, which is rather more subtle, is that a flashlight emits electromagnetic waves that just sort of are all overlapping each other. They're sort of every which way. But in a laser, these waves are called coherent waves. They line up exactly so that every wave is superimposed on top of every other one. And coherent waves have certain properties that make them particularly useful in science and technology, for example, in designing holograms, and also for conveying lots of information, because you can do things with that wave of a laser light that's so controlled that you can't with just normal visible light. These special qualities of lasers find hundreds and hundreds of applications in science and industry and medicine. You've seen them, you've heard of them in so many different ways. Thus, the fundamental discoveries by Bohr and others regarding the nature of atoms and the nature of light-matter interactions have ultimately led to technologies that affect and improve all of our lives. I want to summarize this lecture on Bohr's concept of the atom. Niels Bohr developed a concept of an atom that incorporates electrons that adopt specific energy levels, like stair steps, the ground state, and excited states. Electrons can jump from one level to another, and in the process, energy must be absorbed or emitted as photons. Light and matter interact by this process, as exemplified by the phenomenon of absorption and by the phenomenon of fluorescence. Scientists study light-matter interactions, and by extension, they study the structure and the composition of the natural world using an arsenal of spectroscopic techniques. And finally, we saw that the invention of the laser is a direct outcome, a direct consequence of our newfound understanding of the atomic realm. By now, you're probably beginning to expect that the world of the atom is a strange place indeed, far different from our everyday experience. These differences are formalized in the field of quantum mechanics, which is the subject of the next lecture.